In this video, we're going to define the Fourier transform for digital signals. It's known by the complicated name of a discrete time Fourier transform. It's so long-winded everybody calls it the DTFT. We're going to see that it looks very similar to what we've already encountered, and we're going to talk about its properties, many of which are shared with the Fourier transform we've already defined for analog signals. So this is a fairly easy leap to go into the discrete time world. So let's define it. And like I said, the definition looks very similar to what we had for analog signals. The big difference is, like I keep saying, is that it's a function of f, which has no units, and f is in the range minus a half to a half, or 0 to 1, as the case may be. We'll figure this out a little bit later. I do want to point out the notational change. This is written, the DTFT is written as s of e to the j2 pi f. The variable is f, but this helps us distinguish it from the Fourier transform of an analog signal. So this is the notation we're going to use for the DTFT, and when you see an s of f, you'll know that means an analog Fourier transform. And f in that case has units of hertz. Okay, so again, the all spectra are periodic with period 1, and as we know, that comes from the fact that this is periodic with a period of 1 as a function of f. So it has to be periodic, and I'm going to show you an example to show you how that works. So here's a little simple example. It's a exponential signal, and let's plot it so we understand it. So A to the n, U of n. Okay, the first thing to note is that the unit step multiplies the A to the n. So the unit step, if you recall, is 0 for n negative, and it's 1 for n equal to 0 and positive. And that's going to, the part that's back here for negative n is going to set to 0 the exponential. So the only thing we get is the exponential for positive index values, positive time values. And it may look something like that. If a is bigger than 1, this thing could take off. Still 1 at the origin, but it could get very big very quickly if a is bigger than 1. So what I've done here is shown this example here was a less than 1. Okay, well, let's compute its spectrum. And the way that proceeds is very straightforward. I'm just going to plug in for S. I'm going to plug in what my signal is. There it is. And again, what the unit step does is that it sets to 0 anything for n negative, so I can change the limits of the sum and therefore get rid of the u of n and get a much simpler formula I can play with. And I want to point out that the complex exponential here can be thought of as e to the minus j 2 pi f all raised to the nth. And that means I can merge those two exponentials in the formula. This is going to be the key step to getting an analytic expression for the spectrum. So here's what I did, same thing. And now we have to recall the geometric series. Very important in digital signal processing to know this property. You sum up a exponential in alpha from 0 to infinity, as long as the absolute value of alpha, the magnitude of alpha, is less than 1, it's given by this very concise formula. So I'm going to use that formula because that's exactly what I have here. And this formula works even if the alpha is complex valued. The only thing that matters is that its magnitude is less than 1, which it certainly is in this case if I assume that the absolute value of A is less than 1. All right, so we can use it. Very simple formula pops up. There it is. And so that is the spectrum of the exponential signal. Let's plot it. And for a specific value of A, which we have a half. And here you see the periodic nature of it. You can go between -1/2 and 1/2, or 0 to 1, whichever you want. I want to show you how I plotted those curves for the magnitude and phase. You'll notice I didn't actually give you a formula for the magnitude and the phase. It turns out for discrete time spectra, those expressions can be fairly unwieldy. So just to recall, here's what the transfer function was for our example. The exponential signal. And what I want to show you is that in using modern tools like MATLAB or Octave, it turns out you can basically type this expression in as it stands and get all the information about the magnitude and phase that you want. So let's see how that works. So here I have the MATLAB command window, and I'm going to type in a range of frequencies going between -2 and 2. That's sort of what was shown in the previous figure. And I'm going to say that A is 1/2, which is what we had. And I'm going to type in the formula for H. I want you to notice I'm literally typing it in. J in all. Turns out the default in MATLAB and Octave is that J is equal to the square root of -1. The only thing that's interesting here is notice the dot slash. What that means is term by term divide, because F is a vector, and the exponential here of an expression containing an F is also a vector. And so when you want term by term division, which is exactly what I want, this is the expression you want. You want to put that in. Okay, that's that. I'm going to create a subplot, it's called, in my plot window here, and I'm just going to plot it. Plot F. Now we want to plot the magnitude, and in MATLAB and Octave it's abs function for absolute value. And there it is. Turn on the grid. So, of course, the interesting range is between -1/2 and 1/2. That's the range over which the frequencies are really of interest. The rest is periodic, so you can get everything else is a periodic repetition, just like we've been talking about. So that's negative frequency, that's positive frequency, negative, positive, negative, etc. But notice how easy it was to plot. Just type in the expression for the spectrum, and there it is. All right. So now I'm going to do the angle. Plot, and I'm going to go back and change that to angle. That's the function we want. Now, it turns out this is going to return an angle in radians, and I don't know about you, but I find degrees a little bit easier to understand. So the way to do that is multiply your angle by 180 divided by pi. And also, I should point out that MATLAB and Octave know what pi is too. That's a predefined variable. I didn't have to define it out to very many digits. And here's the I'll turn on the grid. And now we can see that the angle never really gets beyond about 30 degrees. It's kind of interesting. You can prove that the phase at the origin, zero frequency, is either going to be 0 or pi, has to be real valued, and that's going to be the same at a half. Now, at a half may seem a little odd until you realize what the complex exponential is. So if you look at e to the minus j 2 pi f n, evaluated at f equals a half, and we've already done that, that's minus 1 to the n. So when you calculate your spectrum, your DTFT, at that frequency, it only contains real numbers. So again, the phase has to be either 0 or pi, and so phase tends to have this rather complicated appearance to it. But also, let me point out that the phase is odd and the magnitude is even, just like they should be. And both are periodic because e to the j 2 pi fn is periodic. But the real point of this segment is how easy it is to plot very complicated transfer functions once you have a formula for the transfer function or the spectrum that you want. Okay, what's the inverse DTFT? Well, we're going to use our orthogonality relationship that we used a long time ago for the Fourier series, and we showed that the integral for two different indices here was equal to this expression, which we now know we can write as a unit much more concisely than writing it like that. Anyway, same kind of thing follows. We're going to multiply our expression for the spectrum by the complex exponential, integrate, and that will give us back our signal. So deriving the inverse DTFT is very easy. And again, just like we had for analog signals, we can go back and forth between the time domain and the frequency domain using these formulas. We go from time domain to the frequency domain using the DTFT, and the inverse gets you back. So just like we had before, we can think about a signal either way depending on the application. So let's explore some of the properties of the DTFT. None of these should be terribly surprising. Of course, the DTFT is linear because it's just a sum of terms, and you can sum a sum this way or do it directly. So it's linear, very important property. It has conjugate symmetry, which is easy to show. So at negative frequencies, it's the same as the conjugate at positive frequencies. And we also showed through the properties of the complex exponential, because it's periodic with period 1, it's also, what's at negative frequency also occurs at 1 minus f. So the old time delay formula still works. If you delay a signal by in zero values, indices, samples, if you will. That's the same as multiplying the spectrum by a complex exponential having the delay up there. And the other way around, if you multiply by a complex exponential in the time domain, that's the same as shifting the spectrum in the frequency domain by the frequency of the complex modulation. And of course, our old friend Parsifal's theorem still applies. Now, in a computer, the power in a signal is not that relevant, not that important. So this is definitely an abstraction about calling that power, but what else do we want to call it? And of course, you can find it in the frequency domain or in the time domain, whichever is easier using Parsifal's theorem. The proof of this is just like it was for all the previous examples we've gone through. So, the DTFT shares many of the properties of the Fourier transform we've already encountered for analog signals. It's very important to note that all spectra are periodic, and the reason for that is just because of the way the math works out. That's one way of looking at it. And because it has to be periodic, the highest possible frequency you can have in the discrete time world is a half. There is no higher frequency in that because it has to be periodic. We'll get used to that. Now, what we've talked about with the DTFT is how to compute it. We've defined it. Remember back when we talked about signals? There are some signals for which there are no formulas, in particular speech. How in the world did I show you that speech spectrogram several videos ago? How did I do it? I don't have a formula, so it's going to be a little difficult to compute this directly. And how we do that is the subject of the next video.